Okay, so now that we've practiced and applied the use of contingency tables and done some probability calculations using contingency tables, we're going to take it a bit full circle and use probabilities to infer contingency tables to infer probabilities. So that way we can translate from one probability to another through the medium of a contingency table that's a little easier to understand. So when we're talking about probability math, you'll see that it very heavily leans on the idea of a complement. So if I know that 60% of my sample purchased milk, that means that 40% did not. And so if half of the people who didn't purchase milk bought snacks, that would be half of 40 and 20. So there's some things you can calculate by taking complements of probabilities that you do know and infer new things. So for example, if we knew that 3 out of 5 smokers were men, we can ask what fraction of women seniors smoke in high school. So if we got 3 out of 5 of senior smokers are men, what fraction of women seniors smoke? So if we okay, so just in general, we have 1 out of 5 high school seniors are smokers, just as some imaginary data here. So if this were true, that would mean that so because 3 out of 5 smokers were men, that would mean 2 out of 5 smokers are women. So 2/5 of the 1/5 are women smokers. So that's 2/25 in general, or because we're thinking about a population that's split evenly men and women, it would be 2/25 of smokers in general, or 4/25 of women were smokers. So that's going to be a different fraction than men. So we've gone from probabilities, right? We have a probability of smoking and another probability, a probability of smoking assuming you're a man, to a new probability, a probability of smoking assuming you're a woman. So that transition from one set of probabilities to another set of probabilities is an important skill to be able to do, because it's going to allow us to accomplish some pretty cool business-related things like, for example, focus groups. So let's take a look at our contingency table. This is the DVR plasma one from before. But we can do some probability math just going right from the probabilities that were given or implied by the contingency table. So for example, here if I've got the probability of DVR, assuming I purchase a television, times the probability of television, that's the definition, or that is equal to probability of DVR in television. So if all we knew was that the probability of a DVR assuming television was 0.475 and the probability of a television is 0.267, we could use those two probabilities to create a table and then infer the probability of the joint one. So there are other approaches. We can use other formulas. So in this case, now in the second bullet, we're using this, the joint probability as a conditional and marginal twice, right? We use it here and we use it here, and because these two things are the universe of DVR and TV and DVR, or that's the universe of DVR, we can add those up. So it ends up being 4 separate probabilities that we can get to be DVR. So so we can do it that way, but in many cases it is more intuitive to infer a table with observation and counts, even if there was no actual study done. So for example, let's just think about, I'll hop over to Excel here. Suppose I know that the probability of milk is equal to 70%, and then the probability of snacks is equal to 40%. And the probability of milk and snacks is equal to 20%. So I've got milk, no milk, snacks, no snacks. And I'm going to put 1,000 here. And the reason I'm putting 1,000 here is I don't want to confuse observations with probabilities. So if I put 1,000, there will be no confusion. I will always know when I'm talking about observations, when I'm talking about probabilities. So if I have 1,000 observations in my sample, and the probability of milk is 70%, that means there must be 700 milk drinkers in my imaginary 1,000-person sample, and 300 no milk drinkers. That also means milk and snacks is 200, which means milk and no snacks must be 500. And we know the probability of snacks is 400, so that means the probability of snacks and no milk, or the number of people with snacks and no milk is 200, because again the column totals have to add up. And so this must be 100, and this must be 600. So now we have an observation count for all of these locations, and we could ask questions like probability of milk or snacks is equal to we've got 200 in the upper left hand corner that counts. So 200 is milk and snacks. Oh, 200 is milk and snacks. 500 is milk, no snacks. 200 is snacks and no milk, and then the 100 at the end are no snacks and no milk, and so they wouldn't get included. We divide by the 1,000, and we get a 90% probability. So if you look, if just imagine we didn't have this here. Just imagine this is off camera for a bit. I know that milk is 70%, snacks is 40%, and milk and snacks is 20%. How we get milk or snacks to be 90 is pretty tricky. You know, it's not obvious how you would get from here to here, so you'd have to use the definition of some of these things and try to get there. So if we work through a contingency table, we can more intuitively make conclusions, even though we don't necessarily know an actual sample, right? If we did 1,000 observation sample, we would expect to see something like this because it would be consistent with the probabilities we were given. But that doesn't necessarily have to be 1,000 observation sample that exists to make use of the contingency table. All right, so let's turn now and think about how we can consider conditional probabilities and contingency tables and how they map to each other. So suppose I have two events. I have a large customer that cancels an order 10% of the time. So the complement of that is that they don't cancel, which happens 90% of the time. And the firm has layoffs 10% of the time and doesn't 90% of the time. So naturally, both of these could happen. One could happen, the other could happen, or neither can happen. So if we imagine a contingency table, if I do 1,000 things in a contingency table, I'm going to have 100 customer cancels an order, right? And I'm going to 100 layoffs. So in my 100 cancels and my 100 layoffs, a question we could ask is, how many, and therefore what chance, is it where in the cell for layoffs and customer cancels? So we don't know exactly, but just kind of think about the nature of the question and decide whether or not you think the number of both cancels and layoffs is going to be bigger than 10, and therefore the probability will be more than 1%, or will it be exactly 10, or will it be less than 10? So go ahead and give it a thought. Give it your best shot, and then pause it, and then we'll talk. So pause. Okay, hopefully you've made a conclusion now. The reality is it's likely that the chance that both occur is going to be more than 1%, and that cell will have more than 10. That cell may even have 100. So it might be the case that if you have a large customer canceling an order, they will inevitably, 100% of the time, lay someone off. That may not be true, but it certainly could be true. And in any case, it's likely that when orders are canceled, layoffs may follow. And so the chance that both occur is going to be more than 1%. So now let's think about the chance that either occur. Okay, hopefully you've thought about the chance that either occur. Is it going to be less than 20, 20, or more than 20? Well, for it to be more than 20%, we would need every time a customer cancels an order, we'd have no layoff. And even then, if that happened, you would be 10 plus 10. That's the biggest number you can get is 10 plus 10. And the fact is, that's not likely to happen, right? Because these are going to follow each other. It could even be the case that the chance either occur is exactly 10% because they're perfectly correlated. So my choice is between more than 20, 20, and less than 20. Because these should sort of happen together, less than 20 is going to be the answer. Because 10, it might be 15% or 12% of the time one of these happen. It's 10% of the time if they always come together. It's 20% of the time if they are never happening at the same time. And that's not the case. So we're going to ask a couple more of these in a minute in the next video.